In this lesson, we're going to take a look at work energy in terms of gravitational potential energy and kinetic energy, and then apply that to the electric system because we're familiar with gravity. It's a force that we deal with on a day-to-day basis. Now, this picture shows two rocks that each have some gravitational potential energy, and they have that energy because they have height and they're in a gravitational field. They're in Earth's gravitational field, which is uniform and in this direction. And we know that their gravitational potential energy is given by their mass times the gravitational field that they're in, g, times their height. Their gravitational potential energy is mgh. We also know that as these things fall to the ground, the gravity is doing work. And that work is changing the potential energy into kinetic energy. And one way of looking at this is saying that the amount of potential energy that is lost, the change in potential energy, is equal to the opposite of the work that was done by gravity. Because the work done by gravity is positive because it's pulling down and it's moving down as it falls. So force times distance times cosine of angle between them. But the change in potential energy is negative because our change in height is negative. It's going from higher to lower. Now we also know that what's actually happening is that gravity is, yes, reducing the potential energy, but changing it to kinetic energy. So the total amount of mechanical energy is constant. And that makes gravity a conservative force since it doesn't change the amount of mechanical energy. But what I want you to see here is the work done by gravity is opposite of the change in potential energy of the rock as it falls. That's exactly what happens when a charged particle moves in an electric field. So here we have a uniform electric field, and just like you guys mapped in lab, we can see at the edges it bulges out, but we're in the middle, so we have a uniform electric field, and we have a positive charge in that field. And up here it has a high potential energy, and down here it has a low potential energy. Now we can pick the zero height or zero potential energy spot wherever we want, and once we've done that, we have like position B, position A, but we've got our zero. And so over here, this is position B, this is position A. As this charge is pushed to the right by the electric field that it's in, it's got potential energy over here that changes into kinetic energy. It loses potential energy. So its final potential energy minus its initial potential energy is equal to the opposite of the work done by the field. Okay? Well, that's what this equation shows us. The opposite of the work done by the field is right here. And just like we had mgh for gravitational potential energy, what we have here is QED. Well, Q is the analog of mass, but it's charge. E is electric field rather than gravitational field, and D is distance, which is the analog of height. And so all this equation is saying is that the change in potential energy of a charge is equal to the opposite of the work done by the field as it moves that charge. Now, the way I explained this in the handout that we went through was that the change in potential energy of the charge was equal to the work done by something moving against the field, right? So if I did work to move this charge from here to here, that is equal to its gain in potential energy. Just like when you do work to lift a rock higher, the work you do is equal to its gain in potential energy. So these are equivalent equations. It's just who's doing the work. In this case, the electric field is doing the work. In the case that we went through, some outside force was doing the work. But since the electric field is doing the work and it's reducing the amount of potential energy, we see that the change in potential energy is opposite of the work done by the field. What makes voltage different or electric potential energy different is we don't mind talking about mgh. We talk about the energy a rock has because it's up in the air. But we don't do that for electric potential energy. Instead of talking about electric potential energy, we talk about electric potential. And so this is an interesting thing because all we're doing is dropping off the energy and we're saying it's a different thing now. Well, it is, because now when we talk about electric potential, we're talking about energy per unit charge. energy per unit charge, and it's the potential energy a charged particle has due to its location in an electric field. So this is potential energy per unit charge, and this is what we call a volt or voltage. So the voltage at A is equal to the potential energy at A divided by the charge. And then we remember this only makes sense in comparison to another location, right? We have a height, but that height is measured from some 0. We have a position A, but that position A is measured from some 0 position that we pick. And so the volt is actually a joule per coulomb. It's a measure of energy, potential energy per coulomb of charge. And so because we're lazy and we don't want to say potential energy per unit charge, we just cross off the whole rest of this and we say electric potential. So electric potential is potential energy per unit charge, and it gets units of volts. A volt is a joule per coulomb. Now, like I mentioned, only changes in potential energy have any meaning. We have to have something we're measuring relative to. Just like a rock on a cliff has potential energy mgh, but that doesn't mean anything unless we know where we're measuring h from. So we pick some 0. We usually say, oh, it's the level of the ground, and so we pick up from there. Well, we do the same thing when we have an electric field, right? We have a positive plate, we have a negative plate, and what we usually say is, oh, we're going to call this over here, we're going to call this 0 potential energy, and over here this is more than 0 potential energy. And so we have our positive test charge here, and it's got lots of potential energy, and when it gets to here it has no potential energy. Now, this doesn't have to be 0. You can make whatever number you want, and we talk about the difference between them. So this is the same equation before. So the voltage from B to A is the voltage at B minus the voltage at A, and that's equal to the potential energy at B minus the potential energy at A divided by Q, because that's what the definition of voltage is. And because the change in potential energy is equal to the opposite of the work done by the electric field, that's what that is, and then we divide it by Q. So what this shows us is the potential difference between 2 points is equal to the opposite of the work done by the electric field as it moves a charge between those 2 points. The reason we don't use potential energy but rather just potential or potential difference is because we think of masses as discrete pieces that fall, which is great. Charge isn't really like that. This is usually a continual stream of charged particles that are moving through here. And so by dividing out the charge, we make it so it doesn't depend on how much charge is here. It only depends on the strength of the electric field and the distance between them, how far it gets to accelerate in that field. Okay? So we could say that this rock has some gravitational potential, and this rock has the same gravitational potential, even though this rock has more gravitational potential energy because it has more mass. This is a whole bunch of math. Don't let it freak you out. We just saw this equation. We said, okay, the potential difference between 2 points is defined here. So this VBA means the voltage at B minus the voltage at A. Well, voltage is potential energy per unit charge, so that's what that is. And since the change in potential energy is opposite of the work done by the electric field divided by charge, we have this equation. Well, if we just go ahead and multiply every single term in here by Q, we multiply that by Q, we multiply this by Q, we multiply this by Q, then what we have is work equals Q VB minus VA. Now they have this negative out front because they changed the work from negative work to positive work. So what this says is the work done by the electric field moving a charge from B to A is equal to Q, negative Q VBA. And essentially this says the work done is the opposite of the change in potential energy, which we already knew. But since work is also equal to force times distance, and force over charge is what we define electric field as, we can go ahead and make this substitution. We can say, oh, well, force is really just E times charge, and so we also have that the work done by a charge is equal to the charge, or sorry, the work done by an electric field on a charge is equal to the charge times the strength of the electric field times the distance that the charge is moved. So let's look at a summary of the equations we've looked at, and these are all for a uniform field. So we have our uniform field here between two plates. Now it started with our definition of change in energy, right? And so we said, okay, it's got high potential energy here, it's got low potential energy here, and the electric field does work to move this thing from high potential energy to low potential energy. And so a change in potential energy, that's our final minus our initial, is equal to the opposite of the work done by the electric field, and the work done by the electric field is QED. Of course, charge times force, or electric field is force, and work is force times distance. Now, this is our definition of voltage. This is not for a uniform field. This is true of anything. This is a volt is electric potential, and so electric potential is potential energy divided by charge. And then this is the work done by the electric field moving the charge from A to B is equal to the opposite of the change in voltage. Right? So that's delta V, opposite of the change in voltage. And so the voltage at B minus the voltage at A gives me the opposite of the work per unit charge. That's really just these two equations smashed together. And then if we go ahead and multiply this equation by Q, we end up with this equation. The work done is equal to the opposite of the electric potential difference. So this says Q VBA, but it could just as easily have said negative Q delta V. So it's just this equation. We multiplied every term by Q. Then we get back into work equals force times distance. And so on this one, remember, I'm basically just looking at this half of this equation. The work done is equal to the force times the distance. Well, force is electric field times charge times distance. And then this last equation, electric field, is equal to the opposite of the change in voltage divided by distance. Now we're going to look at one more. We've been looking at things in a uniform electric field, but if we have a point charge instead of a uniform field, then remember this field goes out equally in all directions. And so for this one, instead of randomly setting a point of zero potential energy, we say, well, if this is a positive charge, there's no potential energy at infinity. When these are infinitely far apart, there is no more force between them, so there's no potential energy. And then when we do work to bring that charge in closer, it gains potential energy. And so with a point charge, we can find the potential energy relative to infinity, and it's actually given by kq over r, where k is Coulomb's constant, 9 times 10 to the 9th. Q is the charge of the thing creating the field. So the uppercase Q is the charge that creates the field. You'll notice before we were using lowercase q, and that was because that was the charge in the field. In this case, it's the charge creating the field, and then divided by r. You'll notice this is almost kq over 1 q2 over r squared. Well, because we're finding potential difference and work, this has become an R. We'd have to use calculus to show why. And because we're dividing by charge, we get rid of the Q2. We get rid of the charge moving in the field. And so we're just left with this equation. Interestingly enough, we can graph this equation, and that's what these two diagrams show. This is the electric potential due to a positive and due to a negative charge. You can see as the distance gets bigger for a positive charge, the potential energy per unit charge gets much smaller. As we get closer, the force gets stronger, therefore the electric potential increases. Here it looks the same, only it's negative, right? So we have a very big negative potential when our field is created by a negative charge.